Okay, here we're going to solve a Newton's second law problem with a block on an incline. We're going to use Newton's second law, which means we need to identify all of the forces acting on our block in order to calculate the net force, in order to get the acceleration. We will assume we know the angle here, theta. We will assume we know the mass of the block, m, and we will assume there is some friction on the surface between the block and the incline, and we will assume we know the coefficient of friction. From that, we want to find what is the acceleration of this block and how far up the incline does it go before it stops, given that it has an initial velocity, and we'll assume we know that. Now, to use Newton's second law, the first thing we need to do is identify all the forces acting on the block. First thing we do is look at what is the block in contact with. Well, it's in contact with the incline right here. That means there will be a contact or a normal force that acts perpendicular to the surface. And since we're given a coefficient of friction, there will also be a frictional force, and the frictional force always acts in opposition to the motion. Those are the only two objects that our block is in contact with. It has no strings, ropes, cords, pulleys attached to it. And we're going to neglect air resistance. So those are our only two contact forces. Second thing we need to ask are what are the action at a distance forces? And the only one we're going to worry about for now will be gravity. So there'll be the force of gravity pointing vertically downward. Those are our only three forces. From those three forces, we're going to add them up as vectors to get the acceleration of the block, which is a vector, and that equals the net force, F net, which is a vector, divided by the mass, which is a scalar. Now, this vector equation really tells me that the acceleration in the x direction is equal to the net force in the x direction divided by the mass. Mass doesn't have an x direction. It also tells me the acceleration in the y direction will equal the net force in the y direction divided by the same mass. So what I really have here are two equations. And those two equations refer to two separate directions. So what I need to do is identify what do I want to call the x and what do I want to call the y direction. I'm free to pick those however I want so long as these are measured in an inertial frame of reference. Well, right here I have an inertial frame of reference, and I can put it wherever I want, both in terms of where I locate it, namely where am I going to call the origin. I also can take it and I can turn it however I want, and I get to pick the direction I want to use. Well, for this purposes, I'm going to guess the best direction would be to take and angle it so that it is along the incline. So we're going to have the x-axis go up along the incline, and the y-axis will be perpendicular to it. And then what we need to do is simply break all of our components of these vectors into these directions, because we're going to use this as our inertial frame of reference. So that x will be up the incline, y will be perpendicular to the incline. So now what we're going to need to do is take each one of these vectors and find their x and y components. Well, the normal force points along the y direction, so it only has a y component. Friction points along the negative x-axis, so it only has an x component. Gravity, on the other hand, has two components. It's acting at an angle, so it will have a y component and it will have an x component. A little bit of geometry shows that this angle right here is the same as the angle of the incline. Now I know my two components. The x component will just be mg times the sine of the angle, and the y component will just be mg times the cosine of that angle. Now I have all of my components. Now what we're going to do is write down each one of these equations for the net force acting in both directions. So we have the sum of all the forces acting in the x direction will equal Well, that equals the frictional force, which is acting in the negative x direction, as is the gravity that's also acting down the incline. So both of these are negative forces. So I'll put the negative sign in there explicitly. So this is minus mg times the sine of the angle minus the frictional force. That will equal the mass times the acceleration in the x direction. I do the same thing in the y direction. We add up all the forces in the y direction. Well, that will equal, I have the normal force right here acting in the y direction, and I have this component of gravity acting in the y direction. One is acting up along the positive x-axis, the other down along the negative y-axis. So what we can do is say this is the normal force minus mg times the cosine of the angle, and that equals the mass times the acceleration in the y direction, but the ramp will ensure that there will be no acceleration in the y direction. Now we have our two equations from Newton's second law. What we need to ask is, how many of these things do we know and how many things do we not know? Well, we don't actually have a value for the frictional force. We have the coefficient, but not the friction. We don't know the acceleration, that we have to find, and we don't have the normal force. So I have three unknowns and only two equations, which means I need a third one. But we also have a model for friction that tells me the frictional force is equal to the coefficient of friction times the normal force. That is a third equation. So now I have three equations and three unknowns. The rest is mathematics. So what we're going to need to do is solve these equations. So to do that, I'm going to just give them numbers. We'll call this equation 1, that equation 2, and that equation 3. What we can do is we can solve equation 1 for the normal force. Take that value and plug it in right here and solve equation 3 for the frictional force. And then take our value for the frictional force and plug it back into equation 1, eliminate that, and then I have an unknown that only is the acceleration, so we can solve equation 1 for the acceleration. So, let's take and first solve equation 2, which tells me that the normal force minus mg times the cosine of the angle equals 0, and that simply says the normal force must equal mg times the cosine of the angle. My third equation says the frictional force is equal to mu times the normal force, and that will now be mu times mg cosine theta. So now we have the frictional force. Now we need to plug that into the first equation, which told me that minus mg sine theta minus the frictional force, which is mu mg cosine theta, equals the mass times the acceleration in the x direction. That is what we want to solve to find the acceleration. Except we can now notice the mass appears here, it appears there, and appears there. So I can cancel the mass out. Which means in terms of finding the acceleration, I don't actually need to know what the mass of the block is. Now we have the acceleration in the x direction. Notice there's a minus sign in front of everything, so I'm going to factor the minus sign out. There's also a g in both terms, so I'll factor the g out. That leaves me the sine of the angle, plus, because I factored the minus sign out, so plus mu times the cosine of the angle, and that is my acceleration. And since we can assume we have values for g, the angle, and the coefficient, I can now calculate the value for the acceleration. So, our acceleration can be found once we give our values. We will take the coefficient of friction to be 0.2. We will set the angle to be 35 degrees. And we'll also say that starting velocity as it goes up the incline is 12 meters per second. We can now calculate the acceleration. That will equal minus 9.8 meters per second squared times the sine of 35 degrees plus 0.2 times the cosine of 35 degrees. Plug all those numbers in, and we end up with our acceleration being minus 7.23 meters per second squared. Now, we want to find the distance the block slides, given basically its acceleration and its initial velocity. That's a kinematics problem. So what we're going to do is make a table where we put our kinematic variables of time, position, velocity, and acceleration. What are they at the start, and what are they when it ends? Time we can define as starting at 0. We do not know and are not asked to find when it stops. We can say the bottom of the incline, we'll put our origin there. We'll call that x equals 0. What we want to find out is where does it end up stopping, and that's our unknown. Velocity to start out with is our 12 meters per second, and when it stops, its velocity is 0. The acceleration is a constant, minus 7.23 meters per second squared throughout the motion. So what we want to do is find an equation that does not include t, because I don't know and I'm not asked to find t, but does include the remaining variables. And that equation is the v squared equation. The final velocity squared equals the initial velocity squared plus twice the acceleration times the displacement. And we know everything in that equation except the displacement. The final velocity is 0. The initial velocity is 12 meters per second. The acceleration we found from Newton's second law, and the displacement is our unknown d. And we just plug all the numbers into that equation and discover that the d, the displacement, is 9.96 meters. So what Newton tells us, if we have a block sliding up an incline with an initial velocity of 12 meters per second, the angle of the incline is 35 degrees and the coefficient of friction is 0.2, he predicts the block will move a distance of 9.96 meters up the incline before it stops. And that's what we're asked to find. So we are done.